Hello everyone, and welcome back to my programming tutorial series. In this video, I will introduce the Wolfram Mathematica program and go from simple arithmetic to powerful symbolic computations. You'll learn how to use Mathematica as a calculator, how to solve equations, take derivatives and integrals, work with vectors and matrices, create plots, use conditions, and build loops. All right, let's start.
If you don't have Mathematica installed, you can download it from the official site at this website. You can also use a free 15-day trial here. Or you can also try the cloud-based version through this Wolfram Cloud website, which works directly in your browser without installation. Just remember, you'll need to create a free Wolfram ID account to sign in and use the trial or cloud version.
Comments are written between a pair of parentheses and asterisks, like this.
Mathematica can work like the smartest calculator you've ever used. You can type expressions such as 3 plus 5 or 12 divided by 4. When you press Shift and Enter, you immediately get the result. If you type 1 divided by 3, Mathematica shows the exact fraction, 1/3. If you add /n at the end, like 1 divided by 3 /n, it converts the result into a decimal, 0.333. This trick works anywhere, on numbers, roots, or even symbolic results. You can also use mathematical functions, such as square root of 2 or sine of 30 degrees. And remember, trigonometric functions use radians by default, so if you want degrees, you must include the degree symbol, as in sine of 30 degree. This basic calculator mode is your starting point for everything else in Mathematica.
Let's now move from numbers to algebra. Suppose we want to solve the quadratic equation, x squared plus 5x plus 6 equals 0. In Mathematica, we use the solve command. We type solve, then the equation, and finally the variable we want to solve for. When we press Shift and Enter, Mathematica gives us x equals -2 and x equals -3, exact symbolic results. If we instead want a numerical solution, we can use find root. For example, find root of x cubed minus 3x plus 1 equals 0, starting from x equals 0, returns an approximate value of about 0.347. The starting point matters. If we start too close to a flat region or a point where the derivative is 0, Mathematica will display a warning about a singular Jacobian. Simply change the starting value, for example from 1 to 0, and the algorithm will converge normally. You can also convert symbolic results to numbers by adding /n, which tells Mathematica to produce a numeric approximation instead of an exact formula. So solve of x squared plus 5x plus 6 equals 0 /n will return the same two roots as decimals. Before we move on, here's a very useful tip. If you're ever unsure about how a command works, open Mathematica's built-in help system, showing a short description, argument format, and even ready-to-run examples. Also notice that when you start typing a command, such as find root, the text is blue at first. That means Mathematica hasn't recognized it yet. Once the word turns black, the system knows it's a valid command. That visual feedback helps you immediately spot typos or missing capital letters. Mathematica is case-sensitive, so always begin built-in commands with a capital letter. For example, solve, find root, or integrate.
Mathematica is amazing for calculus. Let's take the derivative of sine x with respect to x, using the d command. It returns cosine x. If we take the derivative twice, we get d of sine x with respect to x twice, and the result is minus sine x. Integration works the same way. Integrate of sine x gives minus cosine x. For definite integrals, we specify the limits. Integrate of sine x from 0 to pi over 2 equals 1. And that's the exact symbolic result. If we use /n, Mathematica converts it to a floating number, 1.0. When an exact formula is impossible, we can use n-integrate. For example, n-integrate of x divided by sine x from 0 to 1 gives a numerical estimate. So, d for derivatives, integrate for exact integrals, and n-integrate for numerical ones. 3 commands, and you've mastered calculus in Mathematica.
Now let's solve an entire differential equation. Suppose we have y derivative of x plus 2 times y of x equals 2. We use dsolve to find y of x. Mathematica instantly gives the symbolic solution. Y equals 1 times c times exponential of minus 2x. That's the general solution, which includes the constant c. Now let's go one step further. We'll add an initial condition saying that y of 0 equals 2. Mathematica then plugs that into the general solution automatically and returns the specific solution where c equals 1. This means the complete expression for y is y equals 1 plus exponential of minus 2x. And if you ever need numeric results instead of formulas, you can use ndsolve, which gives tables of numerical data points instead of a symbolic expression. That's especially useful for complicated systems or nonlinear equations. Now let's look at arrays, vectors, and matrices, the building blocks of linear algebra. We define a vector with curly braces. V equals curly brace 1, 2, 3, 4. We can access individual elements using double brackets. V, double bracket 1, gives the first element 1. Let's define another vector. W equals curly brace 5, 6, 7, 8. We can add vectors simply by writing V plus W. Mathematica adds corresponding elements automatically. We get 6, 8, 10, 12. For the dot product, we can use V dot W or dot of V and W. That multiplies each pair of elements and adds them together. 1 times 5 plus 2 times 6 plus 3 times 7 plus 4 times 8, which equals 70. Now, let's move to matrices. We define A as double brace 1, 2, 3, 4, and B as double brace 5, 6, 7, 8. A plus B adds them element by element. A dot B performs matrix multiplication using rows and columns. The result is 19, 22, 43, and 50. We can make it look nice with matrix form, showing the matrices as real tables instead of lists. Mathematica automatically recognizes whether you're working with numbers, vectors, or matrices and applies the correct form of addition or multiplication. Now let's visualize a function. We'll define our own function named f of x. In Mathematica, when defining a function, we must write the variable with an underscore. For example, f open bracket x underscore close bracket equals something. That underscore tells Mathematica that x is a variable placeholder. But remember, you only use the underscore in the definition, not when you call or evaluate the function later. So we define f of x underscore equals sine of x times log of 2 pi x. Then, when we want to use it, for example, to compute f of 2 or f of pi, we just type f of 2 without the underscore. Now let's plot this function from 1 to 9 using the plot command. Mathematica automatically scales and labels the graph. We can also generate a set of sample points using the table command. For instance, pairs of x and f of x from 1 to 9 stepping by half. Plotting those with list plot gives us discrete points, little dots on the graph. Finally, using show, we can overlay both plots together. The smooth analytic curve from plot and the discrete data points from list plot. This creates a clear visualization that combines the symbolic definition of the function with the numerical evaluation of its points, all in one figure.
Now let's look at conditional commands, the if statements. They allow Mathematica to make decisions depending on logic. Let's start with a simple case. We'll define a variable num equals 5. Then we check. If num is greater than 0, print the number is positive. Now let's make it slightly more complex with an if-else structure. If num is less than 0, print the number is negative. Otherwise, print the number is not negative. Finally, let's make a full version. If, else if, and else. If num is greater than 0, print the number is positive. Else if num is less than 0, print the number is negative. Otherwise, print the number is 0. This shows that Mathematica's if command can work just like in traditional programming, making logical choices and guiding program flow.
Finally, let's create a for loop, the classic structure for repeating calculations. We'll build the Fibonacci sequence. First, we define a of 0 equals 0 and a of 1 equals 1. Then we write for. Start with n equals 0, continue while n is less than 10, increase n by 1 each time. Inside the loop, define a of n plus 2 equals a of n plus a of n plus 1. After running it, we use table to display the results. Mathematica prints 0, 1, 1, 2, 3, 5, 8, 13, 21, and 34. The for loop gives precise control over each iteration, perfect when building algorithms or cumulative computations.
Let's review everything we've learned. We began with the basics, how to run commands with Shift plus Enter, and how to use \n for numerical results. Then we explored equations, derivatives, integrals, and differential equations. We worked with vectors and matrices, visualized data, and added logic with if and for loops. Mathematica brings together mathematics, programming, and visualization in one seamless system. If you enjoyed this lesson,
Don't forget to like, comment, and subscribe for more. Thanks for watching, and see you in the next one.
When you modify a plot interactively with your mouse, for example, adding access labels, a title, or changing text style, Mathematica automatically rewrites the command using low-level box structures like raw boxes, row box, and hold form.